is yet another old diploma that you can get from QuestAPlus, or if you just Google released items, this one is from 2009. So the first part of this diploma goes over some thermochemistry. The first part asking to find the activation energy for the forward catalyzed reaction. So you want to remember that activation energy is always from the reactants to the top of the hill. If you have a catalyst, it lowers the activation energy. So we're looking to find the distance from 2 to 1. So that would be A. Moving on to the next one, we have this reaction here. And we can see that we are forming carbon dioxide, but all of this doesn't really matter because it's just saying if you do add the catalyst to this above equation, what would happen? So adding the catalyst would not change the transfer of energy, and it would also not change the equilibrium constant. So everything would stay the same. The only thing catalysts do is speed up the reaction. Our next one here, we have some information about fructose. Then we get some millimoles of fructose burned in a calorimeter. We're told how much water there is and how it increased the temperature. So we are using the formula NH equals negative MC delta T. This side being about the fructose and the other side being about the water. So we can go ahead and fill in some values. One of the things we have to realize is that we do have millimoles and we need moles. So we're going to multiply this by the conversion that changes millimoles to moles. And there's 1,000 millimoles in 1 mole. And then we're solving for H. That's what it's asking for, the molar enthalpy of fructose. And then the left-hand side is all about the water. So negative 250 grams. You're using the specific heat capacity of water and the temperature change. So we go ahead and plug that into our calculator, and you'll see your answer is in joules because that specific heat capacity is joules per gram degree Celsius. So to get your joules to kilojoules, just divide by 1,000, and you should see your answer is D once you isolate H. With calorimetry, if you are studying, make sure you still also know the 3 conditions for calorimetry or assumptions. That is something else that often will come up. So just make sure you have those memorized. Okay, so this next one, we have this calorimeter essentially, and we do have some propane being burnt, and we're seeing how it affects the water. It does tell you that you have an aluminum calorimeter. Now within the question, it's telling you when you go in to do this experiment that you have a significantly different value from the theoretical value. So your experimental value is off. So to make it more efficient, but to reduce the discrepancy, that's a good way to say it, we want to look at what we can do. So using a glass beaker to hold water, that's not going to change anything because we are still losing heat somewhere. Creating an enclosed shield around the apparatus, this seems like an answer. Just let's look at the other one. Rising the aluminum calorimeter above the flame. If you bring it even higher, you would lose more heat. And decreasing the mass of water in the calorimeter, that's really not going to do anything either. So when we're looking at this, the best one is B. By enclosing the shield, you're making a closed system, so we could have less energy escape as heat, and all that heat would be going into the calorimeter. Our next one, during the combustion reaction, energy is blank to the surroundings, so hopefully we know it's released, and the products will have blank potential energy than the reactants. So if it's exothermic, just do a quick potential energy diagram. Reactants have more potential energy than the products. So because it's asking us to compare it to the reactants, it has a lower potential energy. Looking at our next one, it's showing that we know the reaction for photosynthesis and for combustion. So the first part, if you're looking at the reactants of photosynthesis, we are looking at carbon dioxide gas and water, and then it's getting are going to turn into glucose and oxygen. And then the products of complete combustion in an open system. This matters when we're talking about the water. If it's an open system, that means water wants to escape, and it can only escape as a gas. If it is a closed system, water would remain a liquid. So that open system means we want to pick number 5. And the other one, when we have combustion, we always produce carbon dioxide, so number 3, and now water. I like to put it in order, but the other combinations that you could get would be 4-3 and 5-3. So any one of these would be accepted on the diploma, but I just like to put it in order. So our next one, number 6, sorry about this. We have our potential energy diagram, and it's asking us to determine if it's endo or exo. So if we have a rise from reactants to products, it's going to be exo. And asking about the delta H within the equation. If it's endothermic, it is placed on the reactant side. So far I hope you would think this is nice and easy, because it is not that bad. Going to our next one, it has this little long question. We have our target equation, and we have to look how we manipulate. So the first thing I look at is placement. So that big molecule, we have that there. It is on the left-hand side within our manipulated. So far we're just going to keep it as is. The next one, we have H2O2 as a reactant. In our manipulating equations, we have it as a product. So let's go ahead and flip that reaction. So that first one is staying the same. The second one, so I'm just going to rewrite this here. So if this one stays the same, and sorry, it looks very messy, but hopefully we can see it. And the second one, we're going to flip. Okay, now we're flipping it. So just remember, when you flip it, we need to change that sign. Okay, now our following one, we have water as a gas. Now we're going to worry about that in a second, but when we look at our last two, we do see water as a liquid in the equation, and you also have 2 of them. So that means that equation number 4 needs to be multiplied by 2, and we do have the liquid on the product side, so we can keep that in the same place. Now the one above it, once we multiply the second one by 2, then we'd also see that we have this extra 2 moles of the water as a gas. So we'd want that to cancel. So we'd also have to multiply that previous equation, number 3, by 2 as well. So once we do that, we'd have 2H2 plus just 1 O2 to give you 2H2O, and this one is the gas. And then the second one, once we multiply by 2, 2H2O as the gas, plus 2H2O in the liquid state. Now we can see things canceling out nicely. These 2 hydrogens on the product side would cancel with these 2 on the reactant side. O2 cancels, and our gas of water will cancel, and we have everything else we need. So now that we know it will work out to our target, we can go ahead and add all our enthalpies together, and we will see our answer is B. Okay, so the next question, we would need our data booklet. We have this half reaction, and it asks what substances would oxidize. So if this equation needs to undergo oxidation, that means this is a reducing agent. So if this is a reducing agent and we want it to be oxidized, if we were looking at the table on page 7, right? Yep, on page 7, what we would see is OAs are on the left, RAs are on the right. So if we place this on the table, doesn't really matter where, just on the table, we're looking for, and we know it by that, just you'd be able to place it by that potential, we'd be looking for an OA above it. If it was underneath it, it's non-spontaneous and could not oxidize. So our only choice here is A. This is also throwing you off by giving you some reducing agents, but this is a reducing agent, so it can't be those 2. Okay, so let's move on from there. It's just taking a minute to catch up. Okay, so this next one, we're starting to move into some electrochem, and with our electrochemistry, what it's starting with is just being able to assign your oxidation numbers. So remembering that your fixed oxidation number is always, or one of them is -2 for oxygen. So if that was -2 and this was a neutral compound, which it is, then nitrogen would have to be +2. In the second one, if we have -2, but there's 2 of them, this, so far, oxygen will give us -4, so nitrogen would have to be +4. Sorry, I don't know if I said that. It's just asking about nitrogen in all of these. In the next one, again, oxygen we know is -2, so nitrogen needs to still add to 0, and there's 2 of them, so it would be +1. And in the last one, oxygen -2, that gives us -8, shared between 2 would have to be +4. So 2, 4, 1, 4, and it would have to be in that order since it's being specific to the compounds. Now this next one, I was stuck on for a second just because I couldn't find this in the data booklet. But if I read a little bit more carefully, it does say to use this information for the next two equations. So we are taking this value, that positive 66.4, to know the formation of NO2. Now, the other part, or sorry, not oops, not this one, for this one here. But just also recognizing that this formation is for 2 moles forming. So we would just want to figure out what that would be for 1 mole. So just take that number and divide it by 2. And then the rest you can get from your data booklet. So we divide that one by 2 and we'll find that this is positive 81.6. So if you look at page 4 or 5 of your data booklet, you'll see that nitrogen monoxide is positive 90.3. Nitrogen dioxide is positive 33.2, and N2O4 is positive 11.1. So with this, now that we have all of them, again, just realizing we can get this one from the previous equation, divide it by 2 because we are looking for just 1 mole being formed. And then increasing enthalpy, we're going from the smallest to the largest. So we have 4 and then 2. And then 3, and lastly 1. So figuring that out, looking at your data booklet, and just knowing those formations. Okay, this next one, we have the reaction given, and then it's telling us 15 grams reacts, how much energy would be released. So this is an NH equals delta H question, and we want to remember that the H within is going to be the molar enthalpy from the reaction. So it gets confusing because this delta H is not the delta H within the formula. This delta H is energy released or absorbed. So it's asking about PB, so we'll start with that 15 grams of PB. We're going to multiply it by the molar mass, so we can get those grams to cancel. Then we can multiply it by our energy released from the equation. Noting that this value represents 1 mole of the lead. If there was any other substance that we were asked by, because it is molar enthalpy, you would have to divide by the amount of moles. Then you go ahead and plug that into your calculator. That will equal your energy released, and you would see 22.9 kilojoules. The next one is asking about what's happening with when you're taking a look at this. So one of the things that we would look at is assigning some oxidation numbers because it's asking about reduction and oxidation. So we take a look, and the other part is asking about the amount of PB, whether it increases or decreases. So with that, we would know as a reactant, reactants are used up. So that would have to be decreasing. Same thing with this reactant and this reactant. So we are looking for the decreasing, so you could take away those increasing ones. And then the other part is just assigning those oxidation numbers. So you would assign the oxidation numbers. You will find out that PB is undergoing oxidation, and PbO2 is undergoing reduction. So then when we go to answer this completely, we would see that PbO2 is decreasing and that Pb is oxidized. The other part, this is still true, Pb decreases, but this part makes it untrue because it's undergoing reduction, not oxidation. Our next one, again, this one got me stuck for a second because it's not a typical way of asking this question. So at first I was taking it as a half reaction question using cell stoic, just because it's talking about amps and time and all of that. But then nothing was working out and I wasn't sure where to go. So what I did is took a look at some units on page, I believe it's 2 of your data booklet, and you'll see that current is in amps or coulombs per second. So you can make that connection that amps equals coulombs per second. So this is just connecting units together. And now what we can go through is if you have telling that we are producing 600 amps in 30 seconds and we want to know how many coulombs, we can plug in 600 for amps and divide that by 30 seconds. And then isolate the C, and you'll see that your answer is C. So again, this one threw me off because I did definitely want to use Faraday's law and go from there, but it just wasn't working out. So I really broke it down and just looked at the units, and then it made sense. So it's not something you see often. Moving on to our next one, we have the electrolysis of aluminum oxide in an electrolytic cell. And it's telling us that it is molten, so that just means no aqueous, there's no water available. So within it, it's asking about the half reaction for reduction. So reduction is involving the gain of electrons. So already you can rule out A because that's showing loss, and you can rule out C because that's showing loss. Again, you know that because those electrons are on the right hand side. So now we just want the one that would make sense, and that would be B. So if you had aluminum 3 positive and you were going to gain some electrons, so 3 of them, it would form your aluminum as that liquid. If you had oxygen 2 negative and you added more electrons, you are not forming O2. You would be getting a more negative number or ion. That's not really going to happen. Now here, during the production of aluminum metal, the electrolytic cell, anions travel, and this is now just theory. Even if you had a different cell, anions always travel to the cathode. I'm sorry, the anode. Wait about the cathode. Cations travel towards the cathode. And electrons will travel through that wire going to the cathode. So again, know how the cells work, and this is just a nice and easy theory question. Okay, so moving on to this second part of this, we have our 2 half cells. It's asking for the standard potential of the cell, but it's saying that we're changing our reference cell from hydrogen to something else. What does it say? Reactions mature instead. Oh, it's saying it's lead. What this part is, even if we change those values to make lead the reference half cell, so it just shifts the table, you still end up with the exact same cell potential. So we don't actually have to do that. What we can do is take a look at those half reactions. So we have the one with copper, and that is 0.34. And then we have the one with HNO3, and this is a stronger acid, so it breaks up into its ions, and you will find it on the table near the top left as a stronger OA. So this tells us that what's happening in the left-hand half cell is our cathode, and the right one would be our anode. So when we go to calculate the cell potential, even if it is a different half cell, it's still the same. It's still the cathode subtract the anode. So the value that works out here is D. Okay, so moving on to our next one, it's asking in this one, what's your strongest reducing agent? So here you need to just make the table, and if you're in chemistry, you've probably seen this. I feel like this question comes up quite a bit. So you're making your table, like page 7, OAs are on the left, RAs on the right. If you want to make it super accurate, you would also add in electrons, but really we just need placements of those ions and those metals. So from the first one, you would know that PT is the OA, and PT2 positive, and RH is the RA. Because you see products, you know on your table that the PT is going to be higher up than the RH, because you can consider it spontaneous. And if it's spontaneous, OA is higher than the RA. Now the next one is not really telling us much about placement, just because we don't see it on the table compared to PT2 positive or RH. So I'm just going to skip to equation number 3 quickly. And the fact that this says no evidence of a reaction, we know RH is already an RA. So that would mean TE positive would have to be an OA lower than RH, because you don't see any reaction. So it's non-spontaneous. Now I can go back to equation 2. And we do have products, so TE2 positive as an OA would have to be higher up on the table than SM. So now I have my skeleton kind of table happening, but enough to be able to answer the question. So strongest reducing agent, I start bottom right hand, it would be the SM solid. And then the last one, or number 16, which of the following equations represent a spontaneous reaction? So if TE2 positive reacts with RH. We already know no reaction, and we're just going to go through until we see. So SM2 positive, that would be here across from its metal, and PT would be here. That means your RA is higher than your OA, so non-spontaneous. And then PT2 positive is here. TE would be over here across from TE2 positive. Your OA is higher than your RA, so that one's spontaneous. And you can double check D and see that it is also non-spontaneous. So hopefully we can be confident that we have done it correctly. Okay, coming over here, just having trouble getting it. Okay, our next one is giving us some information about zinc going into a beaker. Essentially, you're predicting the reaction. So because you're going into zinc, hydrochloric acid, that is a strong acid. So you have H positive, you have chlorine, so I split it apart because it is strong. You have zinc solid, and you would have water present. So with all this, if we want to know what bubbles are being formed, we need to know what is reacting. So you would just see from your table that hydrogen is your strongest OA and zinc solid is your strongest RA. So if you take a look at those two half reactions, so zinc giving you zinc 2 positive plus 2 electrons, and then 2H positive plus 2 electrons to give you H2 gas. What we can see if we added these two half reactions together is hydrogen is a product as a gas. So we know hydrogen is being formed. And then when it's asking about how it's being formed, it is the reduction reaction of hydrogen. So it is B. So you can take out A because that isn't the strongest, right? It's there, but it wasn't one of the strongest. And we can take out the ones about water because again, water wasn't one of the strongest. It wasn't what essentially predicted our reaction. Number 18 is another question that just shows that you know the theory. If a student were to build a voltaic cell using solid zinc and hydrochloric acid, which of the following equipment would you also need? So within this, because zinc is undergoing reduction, and reduction happens at the cathode, and we don't have a metal present, we would need an inner electrode at the cathode, and also that salt bridge to complete the cell. So the answer is A. When it's asking you about the power source, you really are trying to see if this is spontaneous or non-spontaneous. And from placement of your half reactions up here, you would know that your OA is higher on your table than your RA, so it's spontaneous. Okay, so this question might take a little bit of time. This one's asking which one has the metals being oxidized. So in all of these, you have to take a look at your metal. If it's being oxidized, it is losing electrons. So meaning getting more positive. So with the first one, you would have your aluminum being 0 and your aluminum on the right side being +3. So that is definitely one of them. And you just go through all of them, and the only other one that's going to work is number 4. So your answer is A, and that's 1 and 4, just assigning those oxidation numbers or taking a look at what's happening within the reaction. Our next one, we have the explosion of ammonium nitrate, and it's asking about what's happening to hydrogen. So from here, I really would just assign my oxidation numbers for hydrogen, just so that I know it's what it's asking for. And because it's not changing an oxidation number, there's no losing or gaining. It's not being oxidized, it's not being reduced, because it has no change. Okay, we're going to keep going. So same thing, I feel like this is a common question, old diploma question that comes up. And you have the half cell, and it's telling you or asking you what is occurring at the cathode. So you take a look at what's happening. We see where the cathode is. You do see oxygen going in. Again, if it's the cathode, you're undergoing reduction, and reduction is a gain of electrons. So you want to see electrons as a reactant. So you can take out B, you can take out C, and then we can take a look at the cathode. At the cathode, you do have that oxygen. You don't have carbon dioxide there. The carbon dioxide is coming out at the anode. So the only possible answer here is A. Moving on, just a few more from Electrochem. So we have our half cell, -2.07. And then it tells us, so just this is a reduction half cell, and it tells us that we have one half cell contains aluminum in a fluorine ion solution, so that's what we see here, and the other one is Pb with Pb2 positive. So if it's that, and it's telling us it's spontaneous, you would just want to look up the Pb half reaction, which is negative 0.13, and because this is going to be higher on the table than what we see here, this is going to be your OA, undergoing reduction, happening at your cathode. So as long as we know that, then we can calculate the cell potential of the whole thing, knowing that the Pb goes first, your cathode, 0.13, and subtract the cell potential at your anode, and you'll get 1.94. Our next one, we have the flow of electrons are going from this unspecified metal from the anode over to the cathode. And it's telling us if we are heading that way, the electrons are flowing as indicated, what could the metal be? So we know at the anode, you're undergoing oxidation and you're a reducing agent. So your Kd, or it actually would be down here, is your oxidizing agent. And your oxidizing agents on the table have to be higher than the reducing agent if this is a spontaneous reaction, which it's implying. So you would go through and just take a look, and the only reducing agent that is lower is iron. The rest are higher, and that would make it a non-spontaneous reaction, so it wouldn't be our answer. Same idea. The next one is more theory, knowing that you know how an electrolytic cell works. So number 23, what correctly describes an electrolytic cell. So electrolytic is opposite of voltaic, so it's not spontaneous, it is non-spontaneous. Anions, doesn't matter what, always go to the anode. Cations go to the cathode, so that's wrong. Electrons are gained at the cathode, not the anode. So the one that is true here is C. And then number 24, what is true for both electrolytic and voltaic? Well, not this one, because that's just voltaic, not the second, because that's just electrolytic. Number 3 is still right. Number 4 is still wrong. Number 5 is still wrong. And number 6 is still right. So we are looking for our answer here to be B. Okay, I think we have one more from Electrochem. And usually you'll have more electro and equilibrium acids and bases just because those are the longer units. So in this reaction, it's just asking what our reducing agent is. So here, if you're a reducing agent, you are going to lose electrons. And I could just tell from here, without doing too much work, that the iron got more positive, losing electrons, so that would be D. The other part, just to reiterate, when you're choosing a reducing agent or an oxidizing agent, you're always choosing reactants. Products just help you see what's happening, but choose the reactants. So you would automatically be able to rule out these last two because that's not what's reacting, that's just what we're producing. Okay, so now we're moving into organic. Here we're asked for the name of the compound we see. So we just want to know or remember that this is an ethyl group, this is a methyl group. When you're naming, it's alphabetically for those side groups. So ethyl comes before methyl. The other part, because it's connected, you have to see that cyclo in the word. So this one is going to be D. Ethyl, methyl, cyclobutane. And they have the numbers here, so we do know the placements. We're just filling in the rest. I like these questions when it's just kind of nice and easy. As long as you know your organic theory, the rest should be fine. So being able to identify an alkene, you need something that ends in ENE. So this would be number 1. To identify your alcohol, you need it to end in OL. So this is number 6. Triple bond ends in YNE, so number 4. Cyclic, you need to see the word cyclo, and saturated has to end in ANE, so number 5. So again, just knowing your theory, these questions, hopefully you'll find nice and easy. Let's look at our next one. Kind of the same idea, more theory. If you're an alkyne, you're looking for a triple bond within the main chain, so number 4. An alcohol, an OH group on the main chain, just knowing that you can't pick number 2 because this is actually a carboxylic acid. To be aromatic, you must see the benzene ring, so number 1, and an unsaturated hydrocarbon. Here, you could pick more than one, so number 3 or number 4. So anything that had a double or triple bond in the main chain. Okay, moving on to this next one. So the next one, hopefully you can identify that this is an esterification reaction, and then we're just naming some things within. So the reactant number 1, that is a carboxylic acid with just one carbon, so that would be methanoic acid. Product 2 is actually naming the ester, and the ester, you would know that from, well, actually it's methyl and methyl on both. So this would be methyl methanoate. Type of reaction is esterification, and classification of carbon or compound 2 is number 6. It is an ester. Our next one, so I feel like these are starting to get repetitive. Again, this question I feel like has come up on many practice tests I've seen. So asking what's aromatic, you can pick 1 or 2 because it has to contain a benzene ring. Both are accepted. A carboxylic acid, you're looking for carbon, double bond to an oxygen, single bond to an oxygen with a hydrogen. So number 3. Unsaturated, so double or triple bond, and alphalic means it's all in a line, so not connected. That's going to be number 4. Halogenated hydrocarbon, you must see a halogen, and that's only number 2. So there is a couple other variations, like you could still have a 2 here. I think that's the only one. So it could be 2, 3, 4, 2, or 1, 3, 4, 2, depending on which one you choose, but both of those would work. Okay, moving from here, you have hexene and hexane and hex-1-ene. They're both colorless liquids, and you're adding some, well, it says orange colored bromine. Here, if you remember the bromine test, you add in bromine, and if it is a alkane, the color will stay brown. If it's an alkene, the brown color from bromine will disappear, and the double bond breaks. So here, just going over that, we know hexane is saturated and hexene is unsaturated. So just asking about that. And the next part, being able to discuss, if you add in bromine in the presence of light, that's just your catalyst, hexane undergoes substitution, and hexene, right, would break double bonds, undergoes addition. So the answer there is D, just knowing our reactants. Here's another common question you will often see, just being able to identify what's organic. So going through this, when we have carbon with a halogen, that's organic. Anything with a metal is not. This next one works. An alcohol works. Your oxides do not work. This one works. Metals and CN don't work. Metals and your carbon CO3 won't work. So here it's 1, 3, 4, 6. So you just want to remember your rules of what's organic. Now, another one, just being identifying. So this is asking us to identify an ester group. If you are an ester, you have a chain with carbon double bonded to an oxygen, single bonded to an oxygen with another chain. So this one could be a hydrogen or carbon, either or, but over here it cannot be hydrogen. If it was, then it's a carboxylic acid. So this has to be another carbon and then can continue or become a chain. So the first one is not, because this one was not a oxygen. Number 2 is because we see that link that we need. Number 3 is because you see that link that you need. Number 4 is not, because this is not an oxygen. And number 5 is not. So your answer was A, number 2 and 3 only. The next one we have starting to go into equilibrium acids and bases. So we have our reaction already here for us, and it's just a titration and asking what's the concentration of the OCl ion. So we want that. So going through this, you would see that you have the amount of iodine. So we have the information about iodine. Change it to liters by dividing by 1,000. Multiply by your concentration. Liters will cancel. Now you're at moles of iodine. Multiply by your mole ratio, so what you want on top, over your known, so that the moles can cancel. Sorry, I should say moles here. And then divide by the amount. So the amount here is 0.1 liters. So you'll go through all this, you'll get a fairly small number. So the number you get here needs to be multiplied because this is in moles. And you need to, or sorry, it's moles per liter, and it needs to be in millimoles. So you multiply it by 1,000 because there's 1,000 millimoles, sorry, this is getting messy, per 1 mole. So your moles will cancel and you'll have millimoles. So if you keep that value in your calculator, just multiply by 1,000 and you would get 1.01 millimoles per liter. So just be careful with this one because the answer that you get in your calculator is 0.01005. When you do multiply it by 1,000, just knowing that when that decimal moves over to here, before you drop the rest, that 5 will affect the 0 beside it. So I got this question wrong the first time just because of rounding. So just make sure you're looking out for that. Asking about the Kb of the the OCl ion. Here you would just want to look up the Ka straight from your data booklet, and you'll see your Ka is 4.0 times 10 to the negative 8. And then you just want to remember, if you want Kb, you take your Kw and divide it by your Ka. So 1.0 times 10 to the negative 14 divided by the Ka written down, and you'll see that your answer is A. Then just knowing if it is a weaker base, it's going to be higher up on the table. So this Kb value, when you take a look at it, it would be, sorry, let's go with the Ka because that's what the table's in. That Ka value would be higher on the table than the PO4 3 negative value. So if it's weaker, it's higher up on the table when you're looking at it organized with Kas. Okay, I'm just going to that one. This next one here, we have our 3 reactions, and then it's asking about what's amphiprotic. To be amphiprotic, you have to be able to donate a hydrogen and have a negative ion if you're not water. So the first one doesn't work because you don't have a negative here. The second one, this works. You have a hydrogen, you have a negative, hydrogen, you have a negative, and water. The next one doesn't work, no negative. This last one doesn't work because you don't have a hydrogen. So the answer for that one was B. And then asking when you have Kas and Kb's values were applied to the equation above what is happening. So we have our Kas and asking if it's less or greater than. Knowing for your Kb that this one on the bottom, because this is in order, this one would have your largest Kb. So it's like kind of opposite. So this would be your strongest Kb, this would be your weakest Kb, and this would be in the middle. So you could actually go and calculate those Kb's and compare it. But if we have that kind of general theory, we would see that the answer is C, that your Ka of H2C6H5O7 negative, this one here, is greater than the Kb of the bottom one, because that is the, what am I trying to see here? I looked at the wrong one. Kb of the middle one, C6, the top one. Again, you can actually calculate those Kb's if you wanted to, but if you could figure out that order, that works too. Okay, so moving on to the next one, asking about Bronston-Lowry acids and then conjugate acid and base pairs. So to be a Bronston-Lowry acid, you have to donate a hydrogen. So from the reactant side, this one was donated. From the product side, this one was donated, just because we can approach from either direction. So we can rule out A and B. And then to be a conjugate acid base pair, you are right beside each other on or in your data booklet on your acids page. So that would be C, and because you're also a difference of just one hydrogen. Looking at the next one, we have a sample and we have the pH, and then it's asking about hydroxide. So this is actually an easier question. Don't overthink this. This is what you would learn in grade 11 chemistry. You need the pOH first, so take away from 14, you get 10.62, and then you remember to get the hydroxide concentration, you want to take 10 to the negative pOH. So you just replace that number in, and we would get 2.4 times 10 to the negative 11. So we would have 2B your A, 4B your B, and then 1 and 1, B, C, and D. So 2, 4, 1, 1. Number 34, we have some information, and it is asking us to calculate Ka of an unknown acid. So we want to remember that you have a Ka formula, hydronium squared divided by the concentration of your weak acid minus hydronium. So we can just go ahead and plug some information in. If you know the pH, you can go 10 to the negative pH 2.32 to get the concentration of hydronium, but don't forget that squared, divided by the concentration of the weak base, 0.167, minus hydronium, and you use it if you have it. So we go ahead and plug that into your calculator. Just make sure that you know how to use your calculator. Keep that denominator in brackets to make sure you are going to get this right. And your answer, you'll see, is B. This next one also threw me off. So it gives you an initial concentration and then final. So originally I was starting to set up ice until I realized we don't need it. And within this, because it is a final concentration within equilibrium, that is the equilibrium concentration. So what we do want to do is balance the equation. So N2O4 to give you NO2, we'll need a 2 in front. And then if you set up your Kc expression, which we'll have to use in the next part, no we don't. Never mind. We just had to balance it. And then, oh, you do need the Kc expression, sorry, because we're calculating Kc. You know that it is your products, and if you have a coefficient, that becomes your exponents, divided by your reactant. So we can go ahead and plug in those values. So that N2O4 goes in the bottom. This value would go in the numerator, square it. And once you also balance it, you'll see your answer is B. Okay, this next one, you're also going to use the Kc formula. You have to do a little bit extra because when you're using the Kc formula, you have to have concentration in moles per liter. You would take each of these, divide it by 1,000 to get it to moles per liter, and then divide each of them by 2 because those are just millimoles and we need moles and in liters. So from the first part, you get a very small number. I think I have 575. The next one, 0. Oh, am I going to die soon? 0.0016065, and the last one 0.00187. So again, put your products, make sure to square it, divide it by your reactants that are multiplied, and you would see your answer is 5.71. So I want to go just a little bit faster because I'm hoping my tablet will not die. So going to our next one, we have our 2 reactions, and it asks if you increased CO2, because these equations are related, increasing this, you're going to get more product. If this continues to react, right, we would have more of it. So you would get more product. So when it asks about the concentration of HCO3 negative, it is going to increase and everything is getting shifted to the right. So that answer was C. And then to write the equilibrium law expression, again, we know it's products over reactants to exponents if we have them, but we also want to remember you don't include pure liquids unless everything is a liquid. So that answer goes down to D. Number 38. 38, we have a graph. Again, I feel like this is a common graph that we see in a lot of tests. Sorry, going back down one more. Just asking what's happening within. So when it asks when we first reach equilibrium, so here we're reacting. When we start to go horizontal the first time, that is our initial equilibrium. So that's happening around 4.5. Then what we want to see is, because we have no vertical lines, we know it is a temperature change. If it was one vertical, it would be concentration. If it was all vertical, it would be a pressure or volume change. Because it's all smooth lines, we want to see that the Cl2 is being used up, right? It's decreasing, and the PCl5 is increasing. So that's showing a shift to the left. So if it's a temperature change, if you increase temperature, you would shift to the right. So you would have had to decrease temperature so that you can shift to the left. Our next one, just talking about titrations. Again, I think this is a pretty common question that would relate to graphing. If you had a polyprotic base, so that would be in your Erlenmeyer flask, and that is what you would be measuring. So if you're starting with a base, you would have a starting pH higher, closer to 14. And if you're adding in a acid that's strong and monoproduct, we'd want to see 2 equivalence points because of the base, And then if it's strong, it's ending closer to 0. So the best answer here is C. A doesn't work because you don't have more than one equivalence point, so it can't be that. Following system at equilibrium. Going through this, if you do know the 4 conditions of equilibrium, one is it needs to be a closed system, so we can't have things escaping. So the only one that would show a system at equilibrium would be A. And then this last multiple choice question is asking, oh, did I skip a page? I think I skipped a page. Okay, I did. Sorry, not quite the last one. So looking at our equations, asking what produces the most products to least. This is showing you have an understanding of the Kc value. So when the more you have, or the higher the number, means the more products you have. The smaller the number, the more reactants. So your biggest number here is number 2, and then number 4, and then number 1, and then your most negative is number 3. Okay. Coming over here, when you look at these and ask the strongest conjugate base to the acid with the weakest conjugate base, sorry, let me try that again. We're looking at weak acids numbered above, and if we ordered from the strongest conjugate base to the weakest. So what I did first is just order my acids. So H2SO3 would appear first on our acids page, then HF, then H2S, and then HOCl, right? So this is our order of acids. So if you had the bases listed, your bases, its strongest base, and then as you go up the table, its weakest. So your strongest conjugate base would be the base of HOCl, so number 3, and then we just keep going, number 2, number 1, and then lastly, number 4. So this top one would have the weakest base. So just taking a look at what's there and then ordering it. Okay, now I believe this is our last multiple choice question. So in this one, we have asked what could act as a buffer. To be a buffer, you have to have a weak acid with its conjugate base that also has to be weak. So the first one doesn't work because it's strong, strong, strong. Here we have the weak acid. If you break this into the ions, you would have your weak base. So the only answer that works here is D. Now, if you did try this test on anything but QuestAPlus, you'll notice there's also a written response. We don't do written anymore. It hasn't changed back. So just worry about the multiple choice and get that practice. And then if you wanted to actually Google it and Google this test, you can take a look and see how well each of these questions tested, so you kind of know what to expect. As always, I hope you do find this helpful, and if there's any question I can do or anything other video I can do for you, let me know. If you did find it helpful, please subscribe, and if you are writing your diploma this Friday, best of luck to you.